Okie doke, everybody. Meeting started. Please take your seats. You know where your bathrooms are. Sorry, if you don't have cookies, you're not getting any. So welcome to the November SAC Zoom meeting. We have some presentations today, a couple members and then a guest presenter. We also want to start off with those nice things we call the club announcements. Okay, can you all see my screen? Yes or no? No.
Not yet.
Okay, that's what I was afraid of. Okie doke. That didn't work. Anyway, we're starting off with elections. And for some reason, I wasn't getting the emails from all those people volunteering to take over those positions. Like Dave Dillmore would really like to be replaced. As a matter of fact, he's stepping down for that matter, so we won't have a vice president. I'm willing to stay on board as president. That would serve you right if somebody doesn't pony up for the presidency. Jack Jones has volunteered to nominate himself for treasurer. Kevin Kozel's stepping down. And let's see, so we need a secretary. And secretary is real easy because all you have to do is watch the meetings, take some notes, pass them on to Rick Rotrammel, and he puts them in the newsletter, which is kind of our archive for this. So let's see, Jack, you're not registering good for some reason. Jack, you seldom register good with most people, but I think that's a personal thing and has nothing to do with your electronics. Just kidding. He's an integral part. So if you're listening in, Jack, go ahead and take your notes, and we don't have to see your smiling face. But anyway, we are still open for self-nominating, volunteering, if you want to consider it that, to be president, vice president, secretary, treasurer, equipment manager. There's not a whole lot of stuff to manage. So I think there are some pop-ups, some sandwich boards for the Messier Marathon that would need to be maintained. Also, I have a load of books, and I can hang on to those until the Messier Marathon, and those will be part of our raffle material. And pretty much it. So that would be the property manager, would be pretty simple job. So step up to the line, members. We need your support. But otherwise, we're going to have to just motor on the way we are. So we'll get her done. So anybody, let me see in the chat if you're interested. I'm not seeing anybody stampeding towards the chat to say anything about it. So we will move on for now. Feel free in the chat later on if your conscience gets to you and you feel guilty about not being the president or the vice president. Feel free to say, I'll do it. So we can go on with that. The next meeting will not be until January, at which time it is, if I'm president at that time, we plan to have it at Grand Canyon University. We've gotten permission from them to hold it. I do not know the protocols for having a meeting there, but I figure it'll be at the most a little bit of spacing and maybe a face mask or two. So be prepared. Don't know if you have to state that, yes, you're inoculated. So stay tuned for that. And our meeting schedule next year will come out in the newsletter or a special email. But right now, it appears the January meeting, I think it's pretty much a consensus. We'll have it on the 14th, closest to the dark of the moon. I mean, to the full moon, rather. So if, see, so that'll put us before EVAC again. For any of you who've been tailoring your nighttime viewing Zoom meetings to catch the EVAC meeting, then the following week catch us. Most of the time this next year, we will be ahead of them. So it doesn't make any difference one way or another. It's just like we were a couple years ago. So enjoy. We will also be planning the Messier Marathon out at the antenna site. Again, we have not gotten any better any better site for the marathon unless somebody can come up with it. And a question was asked, do you continue to use Zoom after we start back at GCU? Yes, because I think a lot of our speakers will find that more convenient than driving to GCU, especially if they're out of town. If they're in Florida, I don't think they're coming in. So by all means, yes, we are going to continue to Zoom as well as in person. So that'll make it easier for us to get speakers. And I think for any of y'all really who don't want to drive across town or just feel hinky about meeting yet, you'll be able to still Zoom the meeting. We've been told that, yes, we won't have any problem connecting to the web for that.
Do you know, Tom, if there's going to be a new room, or is it same old room?
That information will go out once we've got it all lined out with GCU. They may require us to have a bigger room such that if we have 20 people there, there's some spacing between us. I don't know yet. So we'll get that information out, hopefully in the December newsletter to everybody. Are we having a December newsletter?
Hello?
Mr. Rotram, are we going to have a December, okay, there you go, you're back on. We're going to have a December newsletter?
Yeah.
Okay. So hopefully we'll have the dates for the meeting and the information on the January meeting location and which room in that newsletter. And if not, we'll send a special email out to all members.
And it bounces.
I think that's you.
It is me. Oh,
Okie doke. And with
sorry, I shall mute here.
no, you're on. We can hear you.
Okay.
Okay, with that, we will switch into the member presentations right at the moment. And Paul, why don't you go ahead and tell us what the ATM was up to?
Okay. Again, I'm going to need a little instruction on how to do this.
Go down to the bottom or the top to the green share screen thing, and you should be able to click into that.
Okay. What do I want here?
You want to, if you have a PowerPoint or photos or something pulled up, you should be able to see them on your share screen.
Okay, hold on a second. Uh-oh. Whoa. Just a minute. Hold on.
Standing by.
It's not on the share screen yet.
Okay. There you go. You got it.
You are, oh, I am sharing it?
Yes, ATM meeting notes, November the 9th, 2021, Paul Lynn,
Okay, hold on one second.
KO.
Okay, this is a short presentation. So are you getting it now?
Yes, we are. Looks good.
Okay, great. We had about 6 people Tuesday night, and I've got just a very small set of slides. Here's somebody in these, Dwight Bogan, Joe Goss, and Matt Luton, and Glenn Nishimoto. Again, we're working on this 6-inch mirror, which we thought was all polished out, but it wasn't. So we're doing some more polishing on it here. And here Joe Goss is trying his hand at it. Now here's one of our spectators supervising over here, Al Stewing, kind of making sure that I don't know what. Anyway, had to get his picture in there. Now, very interesting thing is that Tom Mausden here brought over a thing called a Unistellar EV. You see down here, Unistellar, and this is the scope, which is pretty amazing. It's a 5-inch totally automated scope, which is driven through Wi-Fi from a cell phone. And it has no manual controls down here. Now, the scope, when you set it outside and set it up, it locates the star field, plate solves it, orients itself, and it's all ready to observe. And so then over here on the cell phone, you tell it what you want to see. So the first thing, when we took it outside, Tom had it point to the Andromeda Galaxy, M31, and the scope integrates the images. It takes several images and it slowly integrates them into a really sharp picture. We could see structure and everything in the galaxies, a lot of things you don't see when you're just looking visually. Aside over here, you see Matt pointing at something that looks like an eyepiece. Well, it's not really an optical eyepiece going into the optical system. It's a little monitor actually that you're looking at. So mostly you view this thing on your cell phones, and being that it's Wi-Fi rather than Bluetooth, you can have 10 people hooked up to this scope all at the same time looking at the same image. And of course, only one of them actually controls the motion. I tried to take a picture outside and I will show you that. Again, Matt couldn't keep from looking in the side of that monitor, but actually, we were actually looking at this through our cell phones. So that's my whole thing. This is, again, it's called a Unistellar EV, and it's pretty remarkable in that all you do is set it outside and it orients itself exactly by plate solving whatever stars it sees in the field. Then it goes to the object you want, and it takes several exposures and builds up integrating them. So that's it. I'll leave it there, leave plenty of time for other people to make their presentations. Any questions?
Okay, how much?
I think it's only about $3,000.
Oh,
I think they're closer to, that was what, when they first came out, I think they're closer to 7 now. Because I looked at one pricing, it's like, whoa, that's pricey, but
Okay.
that is a cool toy.
There are 2 instruments that do approximately the same thing, but this one does a whole lot, does far greater than the other one. I can't remember its name. But I looked this up just a couple days ago and I thought it was down around four grand, but you may well be right.
I think,
And it's pretty amazing. It's really worth 7,000.
I think the other one is it Stellina, something like that?
Yes, I think so.
was that Ken, the Nishimoto, or standing there
Glenn Nishimoto.
with the phone up to his face? In
Yes,
that
I think
picture?
so.
Glenn Nishimoto. Oh, I called him Ken all last week, last month. Glenn.
It's
And
Glenn.
and that was the guy with this 7-inch Starfire, former treasurer, on the other side.
Dwight
The big-
Bogan?
Huh?
Was it Dwight Bogan?
Dwight Bogan, yeah. Dwight Bogan.
Oh, yeah.
Okay.
Can you go to that first slide, Paul?
What about it?
Can you go back to that first slide where it shows them all, everybody at the meeting?
That wasn't everybody.
Oh, okay.
Oh, shoot, wait a minute.
They were in that last slide.
It might be in
Oh.
this one if I,
Yeah, the last slide too.
Joe Goss came back and said that it appears the price is $42.99.
Oh, yeah.
So that's even better
okay.
deal.
That's Nishimoto there
Yeah.
and Dwight Bogan. Haven't seen Dwight for quite a while.
Yeah.
About the first slide.
I think that was the first slide.
Oh, okay,
The last slide.
last slide.
Oh, geez. I can't. Hold on.
You'll
I
get
don't
there.
know.
Is
Might
this
need
not-
practice for you.
Can you see this one?
Yeah,
Hold on, let me see if I can. Well, it's a little bigger. Um, Okay. All right, have you got the full slide now?
Yeah,
no, that's the, with
that's the
Matt.
first slide.
That's extremely shaky, out of focus. I was trying to use a flash, but couldn't figure it out.
That's the, I got the first slide. You got the last slide?
This is the last slide.
Huh?
The one
That's-
where you're outside.
Yeah, one outside.
Oh, you can't see that?
No,
I still have the first one.
Oh, shoot, wait a minute. Hold on,
Oops.
just a minute. Let me get that one up.
Did I do that?
Let me try this again.
Adventures in Zoom.
I'm not sure I can do this. Uh, Where's the share thing? Oh, there we go.
On the great little green box.
Yeah, I had it off the. Did you want this? Is that?
There we are.
Yay. So who's who?
Yeah, it's got a focus.
Yeah.
Who's on
Well,
the phone?
that's Glenn Nishimoto, I think.
Nishimoto.
Okay, then Al and who's in the blue?
Tom Marsden is here in the blue jacket.
Okay,
And really, the main, he came particularly also to pick up the jacket, which he had left at the shop last month. And there's Al Stewing, Joe Goss, and
Dwight.
and Matt Luton. And once again, is looking in his crummy little monitor on the side, which is not really, it's not really a direct optical view, but it's instead it's the integrated digital image. Okay.
Okay.
Okey doke. Well, thank you, Paul. And thank Tom Marsden. That is a neat little toy. I'd like to know someone who's actually seen one and used it or has one. It's that's pretty neat. Before I get on to Terry and let him.
Just a second.
Yeah, go ahead.
I'm not absolutely sure that Tom owns the scope. I think he may have borrowed it from somebody because he had just picked it up that day.
Wow, cool.
Anyway, he has access to it anyway.
That's nice. That is
All
cool.
you need.
pretty cool.
That's all you need. Terry, before I let you present, I'm going to let Steve Dotter talk here for a minute. He wants
Sure.
to talk about the Grand Canyon North Rim Star Party. Okay, Steve, you there? Yeah, you're muted. There you go.
I am here. Can you hear me?
I can hear you. Everybody
Yeah.
else should be too.
Yay.
Hey,
I got an email from the National Park Service last week or the week before, and they said they're set on actually having the Grand Canyon Star Party at the North Rim next year. All the schedule dates and everything that are on the website are going to be valid. We're going to be working out safety protocols and access and all that kind of stuff to have people actually there. So if you want to volunteer, if you can get lodging for yourself for a couple of days or for the whole week, whatever, get that first and then let me know. And we'll set you up. And just like normal, on January 1st is when I start taking reservations for free campsites for the week. You get to stay 8 nights instead of the 7 that you're usually limited to. But you get to stay for a week if you set up your telescope for 6 of the 8 nights. The dates are June 18th to the 25th. And we'll be up there one way or another, and I'll have more details once we get things worked out with the National Park Service. So get your reservations ready, or clean up your scopes and that kind of stuff so we can see you up there at the rim. polish up your outreach skills, and which really only require that you are able to identify, find, and keep an object in the field of view and identify it and tell people where it is on the sky. So if you know how to do that, you're qualified to do outreach, especially at the Grand Canyon. It's a lot of fun, and just a whole week of public outreach. So give me my contact information is on the website under the events and the Grand Canyon Star Party, and most of you already know that, but I just got to say it every time in case somebody doesn't. So if you have any questions, feel free to ask or send me an email or whatever. And I highly encourage you to read the webpage, because a lot of work went into that, and it outlines most of the stuff you want to know. If you have new questions, feel free to ask. So thanks a lot.
Thank you, Steve. Appreciate it. I know some of us want to participate, so hopefully spend that nice time at the North Rim. I've been up there for 30 times. I love it. You can't find a better place in Arizona, as far as I'm concerned. Okie doke. Let's move on to Terry Shea. Terry, you have the floor.
All right, thank you, Tom. Let me share my screen here. Let's go there. It's gonna let me do that. There it goes. All right. Okay. So what I wanted to talk to everyone about, some information here with everyone and share. And good evening, everyone. I want to talk a little bit about astronomy vacations, right? So there's a lot of good places to travel for an astronomy vacation. A lot of the national parks are excellent. You got the North Rim, you got Death Valley, Joshua Tree, Bryce, right? A lot of neat places to go. And then you have the exotic places where, you know, Australia, New Zealand, Atacama Desert, right? So this is kind of a in-between place to go. And it's a pretty easy sell to your spouse. When you mention like, hey, let's go on an astronomy vacation, you know, you might get a funny look. But once you mention the destination, it happens pretty easily. And in particular, this is in Hawaii, Big Island, okay? It's actually a pretty neat place to do astronomy. The island itself here, right, you can see here in the middle, it's dominated by two volcanoes, Mauna Kea and Mauna Loa, both of which are roughly a little over 13,000 feet, okay? So there's plenty of height there. And it's kind of interesting on Mauna Kea here, you can kind of see it's the top of it has a lot of little cinder cones. I got some pictures of that, whereas Mauna Loa has the big caldera up there. The road to get here actually slices right through the middle of the island. And, you know, you can get up to either way, and we'll talk about that in a minute. Now, one of the important things you want to keep in mind is where you stay on the island, okay? So rainfall is definitely going to happen. And on the Hilo side over here is the jungly, lush green side of the island, and that's because it just gets a ton of rain, okay? Whereas on the other side of the island here, this is the Kona coast, less rain, but you still do get rain, but less of it. This is where typically a lot of the resorts are built for nice, you know, sunny days and that type of thing. So, you know, your location on the island, you know, it will make a difference. Also, you know, where do the clouds hang out? So we can see here, basically on the mountaintops here, they have the least amount of clouds. And then over here on the Hilo side, we have the most clouds. That's, you know, goes with the green, right? They kind of go hand in hand. So the Kona side of the island definitely is going to be drier, you know, so there's opportunity there. Okay. So one of the things you want to do when you're heading out to, let's start with Mauna Kea, is check the weather. You really want to check the weather before you go. Let's see if I can bring this up. There's a pretty good website for that. If you just Google Mauna Kea weather, Mauna Loa weather, this is a pretty good site. It's very helpful. And just real quick, here is a quick little topo map here. Let's see, let me zoom out a little bit and I can show you just kind of the road in general here. So this is I believe this is the highway cutting across the island. And then right here is the road up to the visitor center. So the road goes up to about 9,000 feet, which is where the visitor center is, okay? And then from there, the road turns to a dirt road for a while before it goes paved again to get to the summit. And we'll talk about that in a little bit too. But basically on the website here, it has a pretty good forecast. And you can see here, looks like the next few nights, they're actually going to have snow up there at the summit. Now, one tricky thing on the website is make sure you set the altitude. The visitor center is actually about 9,000 feet. So if you set that, you can see it's a little more rainy. It has these pretty good little expanders here. So you can zoom in on the more recent days. And you can see tonight actually is a pretty awesome night to be up there at sunset, clear, all the way to about 5 in the morning. So just, you got to pick your night and watch the weather. There's also some other interesting information on this map for things like how windy is it going to be and, additional information, but definitely check the weather. Okay. All right. One of the things on Mauna Kea is going to be the visitor center, and it's at about 9,000 feet. And it's a nice place. Now, when we went in September, they were still in a bit of a COVID lockdown. So not a lot of people were up there, but it does get crowded once, before COVID, right? It gets pretty crowded up there. Now, the interesting thing here also, if you look in the back here, you can see it's a bit cloudy, right? So again, depends on your altitude on the volcano, where you're going to be as far as how clear it's going to be. Inside, they have a nice gift shop. You can get all your kinds of astronomy trinkets and things. Also, I should have swung the camera around because right behind me, they have 3 or 4 8-inch scopes that they use for public viewing. But unfortunately with COVID, they had them locked up and they weren't doing that. Now, to go to the summit, right, it's right past the visitor center and it's a dirt road and then it goes to a paved road up to 13,000 feet. Now, if you read any blogs about this, you may hear about you have to have a 4-wheel drive or it's just a recommendation. You don't need a 4-wheel drive. Actually, as of 2020, they did pass a law that you have to have a 4-wheel drive now to go up. And there is a park ranger sitting right on the road to inspect your vehicle to make sure that it qualifies to go up. Also, they do require you to stay at the visitor center for like a half hour, 45 minutes to get acclimated. Okay. We stayed for an hour, had our lunch, that type of thing, just because of the altitude. So, you do want to get acclimated. Okay. Heading up there to the mountain here you can see some of those cinder cones I had mentioned earlier. And this is where the road starts to get paved again on the way up. In particular, we took this photo. We did a couple things when we got up there. There's a hike up there if you like hiking. One of the world's highest lakes is on the mountain. And, it's very sacred in the Hawaiian culture. So we did that hike. It's about a mile out and a mile back, which sounds pretty easy. But at 13,000 feet, it was harder than it sounds. The steps are a little tougher and pretty lightheaded as we went, but it was a good hike. Okay. Here, we're up here at the top. And one of the things you can also do, it's kind of a bucket list thing if you want. This is actually the summit of Mauna Kea. And if you don't know, Mauna Kea is actually the tallest mountain in the world, right? So you can actually hike up to the summit of the tallest mountain in the world. A lot of people say, well, wait a minute, isn't that Mount Everest? Mount Everest is the highest mountain. Mauna Kea is actually the tallest, most of it obviously being underwater. But you can kind of see the trail here. It goes right along the edge here. right up to the top, and it is a lot steeper than it looks too. That, again, it's a 0.6 mile hike up there, but that 13,000 feet definitely takes a while. Okay, up here on the summit, again, just taking a picture out on the panoramic view there, some cinder cones. Now from here, I turn the camera 180 degrees around, and there are some of the telescopes there. And you can see here, here's that trail in the foreground. It doesn't show up as well. And then there's me at the summit. We did bring our winter coats for this trip. It was probably about 50 degrees at this point, right before sunset. Once the sun went down, the temperature drops pretty quick into the mid 40s, low 40s. So we were very thankful we brought our winter coats. And then you can see up here in the background, this is right before sunset. All the tourist vans here are lining up with tourists to see the sunset. So there's a lot of people up here at sunset. And incidentally, yes, all those vans are 4-wheel drive. That's pretty interesting. Okay, and here's another picture of the telescopes. I think this is the Keck right here. And this is that trail that I said we took to that lake. This is our car parked way out here in the lone car in the parking lot here, but just a good view from there. And then the sun started setting, beautiful sunset, very, very dramatic, just because you're up there above the clouds and everything, really neat. And again, just the sunset. And the sunset one more time. Now, at this point, the rangers up there on the top there start kicking everyone off the summit. They're like, okay, you gotta leave, you gotta leave. Everyone's like, all right, I guess the rule is you gotta leave after 30 minutes after sunset. Now, if you've ever been to Kip Peak, they do the same thing, right? They kick you off the mountain, right? At sunset, they kick you off the mountain. So I was assuming it was the same rules. It's actually not. As we're driving down the mountain, I noticed cars are pulling off onto the side of the road into parking lots. And I'm like, well, wait a minute, what's going on? Because it's nice and clear up here. And, as we saw earlier at the visitor center, it's a bit cloudy. So after passing 2 or 3 pullouts and parking lots, there was one more I pulled into, kind of looked around like, well, no one's telling me I can't park here. So that was pretty cool. So went ahead and set up for the night there, got the camera out, got the camera pointed up at the Milky Way. Everything's good to go. It's looking good. And then the problem kind of kicked in. I didn't realize couple things. All those people we had passed to pull over, they were going to look at the stars too. They don't have a long tolerance to look at the stars. Okay. And I was at kind of the bottom of the hill. And as I set up to take the pictures, cars kept coming down the hill. So I was setting up for 90 or 2-minute exposures, and the cars just kept coming down the hill. Yep, lots of them. So word of advice, try to get on the first pullout you come up to. Don't take the bottom one. And incidentally, I mapped where this pullout was, and this was about 12,000 feet. Okay, so after a while, the cars started clearing out, so I was able to get a few good shots in. Again, this is a pretty nice shot. It's about 2.5 minutes Milky Way shot here. Another one here, this is a 3-minute shot. Turned out pretty good. The interesting thing about looking at the Milky Way from Hawaii is, right, all the good stuff is a lot higher up in the sky, right? We're here in Phoenix, right? Arizona, we're used to stars in certain position, and Scorpius and Sagittarius are kind of low on the sky, right? They're down there near the horizon, but over there, they're a good notch or two higher in the sky. So that was kind of interesting. This is where I parked. I swung the camera around towards Cassiopeia, which is, I think, right about here. And we've got a drometer right here. And one of the cars that pulled over where we did was a tourist star tour van, basically. He turned on his lights at this point. Thank you very much. But it was kind of interesting, right? He had a van full of people. They went up to do the sunset. The guy drives down the mountain a bit here, pulls out his 8-inch telescope and a big jug of hot chocolate, talks to him about the stars, you know, and gets like, you know, $200 a head for doing this. So kind of interesting. Here's a little better shot here once he turned off his headlights. You see Andromeda a little better right here. Cassiopeia again right here. Cygnus up towards the top. And then he finally turned off most of his lights. So I got a little better shot there too. Okay. Then, you know, pointed the camera up a little more, changed the lenses a little bit. Just getting the core here. That the road is actually right here at the bottom. I kind of tilted the camera to get it out there. I'll get it out of the shot. But very nice here, right? You can see the dark pony. That's always a good tell for me to say, you know, how dark is it? If it's dark enough to see the dark pony, you're in good shape. Okay, and then one more shot here. Little wider lens on this one. Okay. The next night was Mauna Loa. Okay. And again, same advice, you know, check the weather, check the weather. The same website will do both mountains. It's kind of cool. And the other interesting thing is, let me get this map up. I had a slow refresh on it here when I was testing this out earlier. So here on the map, this was the road to Mauna Kea right here. A quarter mile down the highway is the road to Mauna Loa. So the two roads are literally right next to each other. One you take a left, the other one you take a right. Okay. Now the difference here on Mauna Loa is it's a lot less developed. The road up there is a single lane road, but it's not very crowded, very nice. It's paved all the way up. So there's no dirt road. You do not need a 4-wheel drive. There's no one watching you basically, but highly recommended as you go up the road here. Let's see if I can, where am I? You definitely want to stop and get acclimated on this road, okay? You don't want to drive straight to the top at 13,000 feet. You know, they tell you, you know, if you have signs of nausea, headaches, you know, blurred vision, stuff like that, get off the mountains, drive down, just go, you know. So definitely take an opportunity to get acclimated. There's a point in the road here where it does a nice right angle turn. There's some microwave towers here. This is a very nice place to stop and just hang out for about 45 minutes. There's all kinds of lava tubes here. This is all a big lava field, and the lava tubes are really neat to see. You can go walking across the lava. As you walk, it sounds like you're walking across broken glass. Very interesting. The lava is actually very sharp. You do not want to fall down on this stuff. It'd be like falling down on a cheese grater. Very sharp. But again, same map, and do the same thing for Mauna Loa. Just check the weather. You can see they got a couple of snowy nights coming. Make sure you set the altitude. On Mauna Loa, the observatory up there in the end of the road is about 11,000 feet. Okay, so you're going to be at about 11,000 feet. And again, looks like they got the same kind of evening tonight up there. Nice, very clear evening for some good astronomy. Okay. Oh, the other thing about Mauna Loa is, for the most part, there are no facilities. Okay. This is a picture at the top here. There is a little observatory up there, a couple of domes. They mostly do, I think, radio stuff up there. And if you look on a Google map, you'll see public restrooms up here. But what they don't mention is there's actually a gate all the way around it now that you cannot enter. So do your business before you get there. Okay. Let's see. So as the sunset here, again, spectacular sunsets. This is one of the little volcanoes on the island. This is looking obviously west. Just, you know, just spectacular sunsets up there. Really neat to see. And again, above the clouds. We also were there just after new moon. So that was kind of the other urgency to get up to the mountains. Basically the first couple of nights we were there, because I didn't want any interference from the moon. So here we just have a little crescent moon starting to set here. Thought that would make a nice picture too. Okay, and then as the sun set, this was an interesting picture just to take of the belt of Venus. If you've ever been down to Kip Peak, they talk about this in one of their evening programs. It's pretty interesting. Basically, right, this kind of blue layer here is the shadow or the terminator on the Earth between night and day, right? So this is the shadow of night approaching, you know, wherever you are, right? So it's kind of neat to see. You basically can see it just about anywhere as long as you have a clear horizon. And up here at 11,000 feet, we definitely had a nice clear horizon. Took a picture here across the way to Mauna Kea. So this is Mauna Kea over here with the other telescopes up here. You can see they're glinting the sun during sunset. The other interesting thing here, you see some little spots over here and down here. These are cars coming down the road. These are the same pattern and phenomenon that ruined the previous night's photos here. So, yeah. Okay. So once we were up there, it got dark really fast, really nice. You know, again, taking some nice pictures of the Milky Way. Got the observatories and stuff in the foreground, just kind of makes a good shot here. Let's see here, up another shot here. And again, it's just interesting how high up everything is. So here you can see Scorpius right here, and the tail's coming down right here. So the tail is, you know, very high up. Usually this stuff underneath the tail, don't really get to see much of that at all. But it was nice and high in the sky, and it's kind of like, you know, getting some new stars there. Interesting enough, if you do go to Hawaii, and I think it's April and May, you can see the Southern Cross on the horizon and the coal stack. You know, those are visible from Hawaii. Just hugging the horizon though, I think. Okay. And then again, another wide angle shot here. And then this one, again, just this is a picture of the tail end of the Scorpion here. So we got the stinger right here, and the hook is coming around up this way. This shot here, we got Sagittarius, we got the teapot right here, right? Here's the handle up here towards the top. And then we have the spout right here and the top of the teapot right here, M22 there, M8 here, got Trifid right here. And again, it's just, you know, I like the altitude in the sky of all these constellations. It was really fun to see. And then kept inching the camera up a little higher with each frame. So here we go a little bit higher. We got Lagoon Nebula down here, right? Sagittarius star cloud, Eagle Nebula, right? And okay, so that was up on the mountain. Also, just if you want something to do, right? You got to have stuff to do in Hawaii too. Over on the Hilo side, University of Hawaii does have their astronomy center there. They have a very nice planetarium, you know, very nice exhibit and stuff. You know, it was worth just hanging out in the afternoon over there. Very nice. The Aimiloa Astronomy Center. Okay, so again, just something to do. There's the front of it basically. There are flowers everywhere. That's Hawaii. So where we were staying was in an area called Captain Cook Bay. It turned out it was very rainy there. It rained most of the nights, but I actually did get one clear night. So I was out on the balcony, also the lanai, and noticed like, hey, I can see the Milky Way. Took this quick test shot here. Just cranked up the ISO, just wanted to see what's going to be possible here. It looked pretty good. I waited for this cloud bank to start to head offshore. So I was able to like get a pretty good shot here. This is right on the coast, basically. It's a 30-second shot right here. Very nice shot. I then said, you know, I think I can get a shot here from the driveway out front. Basically, this is where we stayed, so I wanted to get a shot of that too. So this shot turned out pretty nice. Got some palm trees in there and stuff. And I actually illuminated this with my iPhone. So this is my iPhone waving around, doing the illumination here. I think I got one more here. Again, just kind of a neat photo with the foreground there and everything. And I think, oh, I swung the camera around to get the north side. Now, obviously, this photo has a very terrible defect in it. The shiny blue lights. So the other side of these trees were another row of houses. So I'm not sure if the house over here had some sort of a blue illumination in the back, or the camera just couldn't focus correctly on the sky at this point. But the Milky Way, I thought, was pretty good shot here, nice and dark. We got Andromeda down here too. So that was a nice shot, I thought. And yeah, that's it.
Cool. That was interesting. I think I could even get my wife to go on something like that.
Yeah,
Like you mentioned, that is so cool.
It's pretty easy to convince your spouse, you know.
There was a question down here. What kind of tracker do you use?
Actually, as I mentioned before, I actually don't use a tracker. I use a Pentax K100. It's a DSLR camera that actually has the tracker built into the camera itself. So, I mean, I do use it, but it's built into the camera.
Oh, okay. Cool. I know you had mentioned that before, but I'd forgotten that was kind of like auto tracking within the camera. That's neat. That is
Yeah,
very,
it is. It
very
definitely
neat.
lightens the load for travel. So pretty much all I have to do is travel with a tripod, the camera, and my 3 lenses. And that's it.
What's the name of that again? The camera?
It's a Pentax K100. I'm sorry, K1. Sorry about that, K1.
Okie doke. Well, anytime you want to present more, by all means, because those are always good. Okie doke. Rick, was it anything you want to say from the newsletter group? You, yourself, and you. He's shaking his head no. So for those of you who can't see, so guess what, Kyle? We're not going to make you sit and listen to us drone on and on about Saguaro Astronomy Club this and Saguaro Astronomy Club that. So for those of you tuning in, all of the attendees, we appreciate it. Cal Massingale, did I pronounce that right? Okay, good. Is from ASU. He's a PhD candidate, and he's big into radio astronomy. I asked him earlier, does he have a telescope? No, he's not a real astronomer then if he doesn't have a telescope. We all know that. But he has a radio. Who doesn't have a radio? I've got several radios, so that's got to be the case. I'm sure I'm now a radio astronomer. Okay, maybe not. But I know that if I have my radio tuned to a static, sometimes when the comets shoot through, you can actually hear them. So I've heard that. I haven't heard it yet. I've tried it with my shortwave radio out there, but maybe some other time. So anyway, Kyle is going to talk to us about the near infrared instrument on the James Webb Telescope that we're sure will launch this December, because everybody knows that somebody's going to die if it doesn't. Well, never mind. Originally, he was going to talk, his subject was a search for SZE halos around high Z QSOs. But how many of us have heard this time and again, that subject? So I'd rather hear about the near infrared. That was a poster session he had done for AAS, but that's the only thing I could find on him for what he's published. But that I read the abstract, and okay, maybe we shouldn't go with the SZEs. My ZWO is complicated enough for me. So Kyle, you have the floor. Run with it, buddy.
Thank you. Thank you. What's my timetable, if you don't mind me asking?
Well, as long as you want to talk, half an hour to 45 minutes to an hour. I have to get up at 6 in the morning, but other than that, you can run for as long as you want. We may lose people along the way, but screw them.
Well, I'll try not to keep you up too late. Well, thanks for that introduction and looking up my poster session from the other year. If I come back, we should have a conversation about amateur radio astronomy. I've done some amateur radio astronomy, and it's something that you can do. I guess the main thing you have to find is amplifiers. But I at one point made like a bucket with some flanges that were sensitive enough to get some emission from the Milky Way.
Now, that
But
would be
anyways,
cool. That's all I need is one more hobby
right,
within
exactly.
the astronomy field.
Yeah, we could give you more astronomy hobbies for sure. But I thought it'd be fun to talk about JWST because it's coming up, right? JWC is actually going to launch very soon here. It's been the telescope of the future for like 30 years now. And so maybe sometime in the next year, JWC will be the telescope of the now rather than telescope of the future. So fingers crossed on that. But I want to talk about a little bit about my own work, but also the one of the science instruments on the JWST, particularly the mid-infrared instrument, which is called nicknamed MIRI on JWST. So just a little bit about myself. I did my undergrad at University of Arizona. I got a BS in physics, and I worked for the astronomy department there for about 3 years. And I worked on the Event Horizon Telescope project, which you've probably heard of, which was a really big radio astronomy collaboration. And so I got to do some of the instrument work on Event Horizon, which was a really great experience. Now I'm a PhD candidate over at ASU, and I've also interned with NRAO, National Radio Astronomy Observatory. They have, Tom was mentioning Green Bank Observatory, which of course NRAO is involved in Green Bank. But yeah, so that's just kind of an overview of what I do. So I'm both interested in the sort of nuts and bolts instrument side of things, actually sort of building radio astronomy instruments. There's a nice candid shot of me soldering something. And then I'm also interested in actually, astronomy observing and learning about new science from observing the stars and galaxies. The only thing I don't do is I don't do any theoretical astronomy. That's not my area. And maybe you've talked to theoretical astronomers, but they're a little bit different. But let's talk a little bit about some of the observational astronomy that I do. And so one of the kind of bigger questions I'm trying to answer with my research is, are high redshift galaxy clusters similar or different to low redshift galaxy clusters? And so, there's clusters of galaxies out there, and some of those clusters are closer to us in the low redshift regime, and then some of those clusters are further away from us in the high redshift regime. So here's an example of a cluster galaxy member from the Virgo cluster. Virgo is pretty close to us, relatively speaking, in extragalactic terms. And so what's happening here is that this galaxy, this is a combination of a few different wavelengths, but let's pay attention to sort of the background, which is the optical that you'll be more familiar with. So there you can see stars, but then you can see a galaxy in the background here of this image. And then the red is CO, which is going to map for us molecular gas, which you may know is like the fuel for forming stars. You have to have molecular gas to make new stars. So what we notice in this image here is the optical and like the CO are not in the same place, right? This is, so what's happening here is this galaxy is falling into a cluster, and while this galaxy is falling into a cluster, a bunch of its gas is getting stripped off. So gas is much more diffuse than stars. You know, stars are nice and dense. It's pretty hard to pull a star away from its galaxy, but it's actually possible to pull the molecular gas away from a galaxy. And so that's what's happening here. And that's what the red. So this is an extreme example of what we call ram pressure stripping. And so this infalling cluster galaxy member is having its molecular gas stripped away from it. And that's the red stuff being stripped out. And so one of the things I'm trying to figure out is this, we see this happening in nearby galaxy clusters and low redshift galaxy clusters. Is this happening at high redshift? And so as you can imagine, looking at galaxies much farther away, you know, we're not going to have as nice a pretty picture as this. We're going to kind of have some blobs that we have to interpret maybe a little bit more quantitatively. So here's an example of a high redshift galaxy that might be undergoing some stripping the way this galaxy is. And so the blue here is sort of contours for where the stellar emission is. And then the pink here is sort of where that molecular gas is. And you can see there's sort of a tail coming off of it. So that might be a sign that this gas is getting stripped away. And so why is all this interesting to us? It's interesting to us because we want to know sort of where stars are being formed and why. Like, you know, why might one galaxy not be forming as many stars as another? And so if a galaxy is undergoing this stripping, then it's not going to be forming as many stars because it's losing its molecular gas, which is the fuel for star formation rate. So yeah, here's some of the galaxies that I've observed. The pink here is the molecular gas that we're looking at in the radio wavelengths. And then the sort of white and black is the optical that something like the HST is looking at. And so we're comparing sort of the stellar disk to the molecular disk. Just briefly, I want to mention that we're looking at these galaxies over different wavelengths, and that's going to, like, we're going to learn a lot more about these galaxies because we're looking at them over a variety of wavelengths. And so this GIF here is showing us this galaxy down here, but with observed from, 87.4 to 87.6 gigahertz. And so we could actually learn about the kinematics of the galaxy by observing it at different frequencies like this. So here's an example of a galaxy. So we call this moment one integrated intensity. And all that really means is we've color coded the frequency, the different frequencies that we're observing this galaxy at. And so, and then we've moved that into sort of the velocity regime, right? So if, because of redshift, a rotating galaxy, well, if it's rotating and we're looking at it, we're going to see it at a slightly different frequency on one side than the other. And that's exactly what these colors are telling us. It's saying like the light on this side of the galaxy is, more blue, is blue shifted, whereas the light on this side of the galaxy is more red, it's red shifted. And that's because of the rotation of the galaxy. And so if we can observe that, then we can learn some stuff about the kinematics of this galaxy. And by understanding the kinematics of the galaxy, we can figure out whether it's having its gas stripped away, and that's affecting whether or not it can make stars. So yeah, so all of this research relates a bit to the idea of star formation rate, which is in any particular galaxy, how quickly is it producing stars? This is like of great interest to us in astronomy. So that is going to transfer us to talking about JWST, because JWST is going to help teach us about the star formation rate of these far away high redshift galaxies.
Quick question for you.
Yes, go right ahead.
You said it was over a wide frequency, but it was 87.45 to 87.62 gigahertz. What is unique about that particular gigahertz range? That seems like an awfully tiny range.
It is a pretty small range. And so these observations are made with the Atacama Large Millimeter Array, the ALMA telescope array down in Chile. And so it's a very powerful set of telescopes. And so it can give us like pretty good, it can give us pretty small bins of frequency information for the galaxy. And so, you know, a galaxy is spinning, but relative to the way things move like in the universe, that spinning is actually kind of slow. So we have to look over a pretty small frequency range to see the redshift differences from one side of the galaxy to another. And so that's why this frequency range is so small.
Ah,
That
okay.
question, is that frequency showing us a particular type of molecule or what?
Absolutely. So this is one of the transitions of the carbon monoxide molecule. And so the carbon monoxide molecule, as far as we understand it in astronomy, generally there is a certain amount of carbon monoxide around molecular gas region, molecular gas being H2 regions. So H2 molecular gas, which is the fuel for star formation, is very difficult to observe. So instead we observe what we call tracer molecules, which carbon monoxide is one of these tracers. So carbon monoxide tends to hang around molecular gas at certain densities. So we can observe a transition of carbon monoxide and get an idea of about what the molecular gas is doing in a particular galaxy. So yes, this frequency is the carbon monoxide transition of the gas in this galaxy redshifted to our observation. Because these galaxies are in redshift about 1.6. So the frequency has been shifted.
Okay, thanks.
Great, thanks for the questions, guys. All right, yeah, so let's talk about JWST, which is going to uncover a lot for us when it comes to star formation rates in these galaxies. A brief overview of JWST, which I'm sure most of you have at least a passing familiarity with. JWST is going to be like our new most powerful space telescope. It's going to specialize at observing in the infrared regime. It has a much bigger mirror than a Hubble and a much bigger mirror than Spitzer, which was another infrared focused telescope. And we believe is going to launch in December. Here's a quick look at the electromagnetic spectrum. Hubble was mostly an optical telescope. But James Webb will be primarily an infrared telescope. And the main decision to have it specialize in the infrared regime was made because the galaxies and stars from the early universe, their light will be redshifted from the optical into the infrared. And so that is why JWST is going to be like really good at observing sort of these, super early universe stars and galaxies because it's at the correct frequency for observe that. It also has like a really large aperture, a really large primary mirror. It's much bigger than Hubble. And then Spitzer, which was another infrared telescope, was even smaller than Hubble. So it's many times more powerful than Spitzer. Quick look at, there's two sides to the JWST. So there's the observing side or the cold side. So this is the part that is blocked from the sun's light by the sunscreen, by the sun shield, sorry. And so this is where you have your mirrors, your instruments, and then down here facing the sun is where you have your antenna to communicate with Earth, your solar power, and your star trackers, so you know like where you're pointed at. And so here's just another look at that. So you get an idea of how big the difference is between the cold side and the hot side. Space kind of does this extreme stuff. The hot side is always going to be facing the sun, and it's going to be at like 200 degrees Fahrenheit. Meanwhile, the cold side is always going to be in the dark, facing away from the sun, and it's going to be like negative 400 Fahrenheit, which is like 50, 60 Kelvin. Where is James Webb going to be located? Is going to be located at the Lagrange 2 point of the Earth Sun system. And so, you know, we don't have to spend too much time but talking about Lagrange points, but basically it's a point, a stable sort of gravitational point that the Webb telescope can orbit. Look at how this lines up. The sun shield of James Webb Space Telescope can be pointed directly at the sun and incidentally directly at the Earth. So it's going to block the light from the sun from bothering the instruments and the science that we want to do. It's also going to block all of the light from the Earth and the RFI from the Earth. So, you know, it's going to be very sort of quiet on the cold side of the James Webb Space Telescope. And the downside of Lagrange 2 point is it kind of puts a hard limit on how long the mission can be because you need some propellant to keep you there. And then also, I'm sure many of you know when Hubble first launched, there was a problem with the focus of one of the mirrors and they had to go up and repair it. That would not be possible with James Webb Space Telescope. So everything has to be perfect. Otherwise, it won't work because it's out, you know, it's far away. There's no bus to catch. There's no space shuttle to catch to go and do a quick repair run. So everything's got to be pretty perfect.
Are there a lot of other satellites hanging out there at L2?
Not that I'm aware of. I think there's been some other projects that have gone to L2 for more solar system science, but I don't think we've ever put an observatory at L2, at least not that I'm aware of. How are we going to get there, right? We got to go pretty far away. Well, the JWST is going to fold up into this origami-like thing, so it can fit in the fairing on top of this rocket. And then December 18th, hopefully, we shall have liftoff. JWST will start making its about a month-long journey from the Earth to the Lagrange point. So, as I said, it's folded up like a piece of origami. And so as such, it has to unfold, and it's going to do that along its way to Lagrange 2. Let's see. Can you guys see my YouTube window? Is that, I get a
Yes,
head
we
shake?
can. Yes, we got
Okay.
it.
Excellent. Let me speed this up because I don't want this to take all day. But okay, so James Webb is leaving the orbit of Earth and it's starting to unfold. For one of the first things that unfolds is the solar panel, so it can get power and start. Then it's going to do some course corrections. You know, I'm not an orbital mechanics expert, but yeah, there's some course corrections that have to be made. It's going to deploy an antenna so it can better communicate with Earth. More course corrections. And then here's where we should be starting to get into the fun stuff. Yes, so now it's going to start unfolding that big sort of sun shield. And so it does it one side at a time. Here comes the other one. And there we go. Yeah, it's also got to lift the mirror up and away from the sun shield. And then those are going to start unfolding, and it's a multi-layered, so it's going to take a little bit of time. But obviously, this was a huge engineering project to sort of visualize this, design it, test the parts that they could, you know, all in a clean room once they were working with flight hardware. So it's quite a feat of engineering. So the media has been calling this, you know, JWST's, you know, 29 days of terror. They've been using colorful phrases like that. This is what they're talking about, is just like, the unfolding of the telescope is very complicated, and it's doing that over a course of a month, and all of it needs to go right in order for JWST to be successful. And so here comes the primary mirror. One thing that they're not going to show you in this is all of these mirror panels need to be realigned once they're deployed. And so there's an instrument called NearCam that's basically going to take a picture of a bunch of stars, compare them to star maps, and then start to do like very sort of micro movements of the panels to get all of the to get the primary mirror in perfect alignment. So that's one thing they don't show you here, but they do show you most of what's going on here. So anyways, there's your 29 days of terror that you've probably seen mentioned in the media. Let's move forward. Okay, so JWST kind of started as this, right? It started as, let's look at some of the earliest stars, earliest galaxies. Let's look as far back in the past as we can. But when you need to scrape together $10 billion, you can't just tell them that your telescope's going to do one thing. It's got to do a bunch of things because a lot of money went into it. So in addition to sort of studying the dark ages, the end of the dark ages, it's going to study the assembly of galaxies. We're going to talk about why the mid-infrared capabilities of JWST make it particularly good for this, because in the mid-infrared wavelengths, dust in galaxies is, you can see through it in the mid-infrared wavelengths where you can't in the infrared wavelengths. And so that's going to make that's going to be a great capability for JWST. That is going to it's also going to use that looking through dust ability to see the birth of stars and protoplanetary systems. So it's going to look through those dust clouds and see what's going on when stars are born. And then, of course, it has to study exoplanets because exoplanets are very popular. And so it has some coronagraph capabilities to ideally directly image some exoplanets as well as sort of indirectly detect them. Okay, here are the 4 instruments on JWST. These 4 are 1, 2, and 3, NearCam, NearSpec, and NearISS are all near-infrared instruments. And then the one we're going to focus on today is the one mid-infrared instrument. Yeah, so let's start talking about MIRI, the mid-infrared instrument. So it's JWST's only mid-infrared instrument. It goes from about 5 to 28.5 microns in the wavelength regime. It's also the only cryogenic instrument. So I mentioned that the cold side of JWST is like 50, 60 Kelvin. Well, in the mid-infrared regime, to have a sensitive instrument, you need to be even colder than that. Otherwise, your instrument is just going to be seeing the noise, you know, from the mirrors, from the detectors. So you need it to be colder so that there's less noise contributed by like your actual physical instrument, and hopefully you're actually just seeing what's out in space. So there is a cryo cooler just for this instrument that takes it from that 50 Kelvin of the instrument, other instruments down to about 7 Kelvin. MIRI is actually 2 instruments in one. They wanted 2 mid-infrared instruments, but they only had enough space for one. So they did a bunch of engineering and basically stuffed 2 instruments into the package of a one instrument package. It's got multiple observing modes, which we'll go over, and it has some good science goals: direct imaging of exoplanets using chronograph, ellipse and transit spectroscopy. So that's going to detect exoplanets by seeing the light that they emit and absorb from their parent star. It's going to study the birth of protostars, and then it's going to study the star formation rate of dust-embedded galaxies out to a redshift of 2. And so if we go back to earlier in my talk where I talked about how I'm interested in star formation rate and what's going on in high redshift galaxies as far as their ability to still form stars. This is kind of why I'm interested in the data we'll get from JWST and MIRI specifically, and Bohr, of course. So it has multiple observing modes. It can just image stuff, so basically work like a very fancy camera. It can do low resolution and mid resolution spectroscopy, and they can also act as a chronograph by sort of, looking at a star, blocking the bright light of the star, and then seeing what's around it, hopefully some exoplanets. Let's get a little bit familiar with the physical setup of MIRI. So here's sort of the diagram, if you will. So I mentioned that this is a cryogenic instrument, so it's cooled down to colder than all the other instruments. And so because of that, it has this carbon fiber hexapod, which is a fun name. Basically, it attaches it to the telescope physically while isolating it from the temperature of the, it's a thermally isolates it from the other instruments. I said it was 2 instruments in one. Here is one of the instruments, that is the imager side. So this is going to look a lot like a camera to us. And then up here, this big box is the spectrometer side. And so that's got lots of complicated optics that we'll take a closer look at to actually sort of view objects at multiple different wavelengths. I mentioned how I was looking at galaxies at multiple different wavelengths, learn more about them. So that this spectrometer instrument is going to have the capability to do that. And there's the mirror for light coming in from the telescope to go in. And okay, so here's the sort of diagram of where the light is going in MIRI. We won't harp on it too long, but there's this pick-off mirror that then sends light to each of the different instruments. Most of the light goes into the imager, which is, MIRI's camera. But then, say about 25%, give or take, of the light goes into that spectrometer, which is that big box on top of MIRI. Very briefly on the detectors, it uses silicon arsenic detectors. We're not going to get into the device physics of it tonight. But this is the same fundamental detector technology that was used on Spitzer, but much bigger arrays. These are much more powerful detector arrays, but they're building on technology we've previously successfully sent to space on Spitzer. Now let's take a look at one of the 2 instruments on MIRI. So we're going to start with the imager, which is the simpler of the 2, as we'll see. And so we're just going to have a bit of fun looking at how the light actually travels through this imager. So here's MIRI. It's sort of upside down from the way I was showing it to you before. There's the hexapod. There's its mirror right there where it lets in light to the instruments. And then down here is that big spectrometer. And right here is that imager that we're about to get a closer look at. Okay, so light comes in from the telescope. It hits the pickoff mirror, and then the pickoff mirror sends it into the imager. We're now inside the box of the imager instrument. And so then it's going to focus that light into this filter wheel here, which has a number of positions for depending on which frequency you want to look at or what type of imaging mode you want to be in. But this filter wheel can rotate to different filter selections, more focusing, and then it lands on that detector array that I was showing you before. So the detector array, for an analogy, the detector array would be like your digital sensor in a digital camera or your film in a old style camera. So there you go. That is It's essentially a very fancy camera. And so that is how light travels through the imager of MIRI.
Do you lose any resolution with all that light bouncing back and forth?
Yes, yeah, there's loss at every stage. Obviously, it's mitigated a little bit by, just really careful engineering and the fact that it's a cryogenic instrument. These mirrors are as cold as we can make them. But yes, there's inherent loss in the system at each bounce. But the number of bounces here is going to look very kind compared to when we see the next instrument, which I'll get to in a second. Okay, so here's the diagram of MIRI. You can see sort of where it lets light in that filter wheel. Let's take a little bit of a closer look at this filter wheel because I think it's really cool. So this filter wheel has 18 stations. It has 10 imaging filters. So those are just going to allow a particular frequency band in. For chronograph diaphragm filters, so that's going to allow chronography by blocking out a central bright source. It has a prism for doing some low resolution spectroscopy. And then it has an open one of these, a closed one, and a lens. And these last three are mostly for, calibration and checking that everything is working fine. Yeah, here's the frequencies. If you were to propose to do an observation with the MIRI imager, you would sort of select the frequency, the filter that you're interested in, the frequency range you're interested in, and then that's where you would be imaging your object. And I mentioned 5 to 30 microns, as you can see here. And so these are the filter coverages. Okay, I said there was 2 instruments on MIRI. Here is the medium resolution spectrometer, which is the much bigger of the 2 and much more complicated. So here's sort of the signal diagram, but let's have some fun and look at the animation here. And do not get scared if you get lost because this is very complicated. But okay, so here's the medium resolution spectrometer down here. We're spinning around, and those are the 2 detectors arrays. The spectrometer needs 2 detector arrays. Those are them down there, and then they're hooked up to their readout. Okay, so light goes through the pick-off mirror, and then it's going to go through relay optics. Again, part of the reason this is designed like this is because they had to fit basically 2 instruments into the size of a 1 instrument package. And so that created some strange optical needs. And so this section right here that you just saw is the relay optics that gets light from the pickoff mirror to the spectrometer instrument. Okay, here we go. Here's where things are going to get more complicated. Whoa, 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 what's going on here? All right. So light has entered into the spectrometer instrument, the medium resolution spectrometer, and it has hit a series of filters. These are dichroic filters. So what these filters are going to do is they're going to reflect a certain range of frequencies, and then they're going to transmit a certain range of frequencies. And so there's a set, it's going to hit a set of them, and it's going to take our broadband light, it's going to split it into 4 different colors by using these dichroic filters. And then from now on, everything that happens to one of these colors of light is going to happen to all 4 of them. Okay. And then, okay, then we got to maybe jump back a little and explain what just happened there. Okay, so back to our dichroic filters, we understand that our light gets split into different colors. Okay, and this is called the IFU, or integral field unit. And so what this does is that color of light that we've selected hits this thing, which is called an image slicer, and it's going to slice that light up into a bunch of different sort of sub beams. And so what that allows us to do is it allows us to do the spectrometry which we'll get to in a minute, but it allows us to do the spectrometry while maintaining the spatial information. So we want to know what's happening in our image at different wavelengths, but we also still want to know sort of where everything is in the sky. And so that's what this image slicer does for us. And so we split it up into 4 different colors, but now we have to do the spectrometry. Okay, so this is kind of the last step here. And so these are diffraction gratings. So I think if you go back to your early physics, what these are going to do is they're going to split the light into much smaller bits of frequency space by, it's going to reflect the light and it's going to diffract it like a prism, right? If light goes through a prism, the path length of the light becomes dependent upon frequency. And so that's exactly what's happening against this diffraction grating. The path length of the light is going to change based on frequency, just like it would through a prism. So we're going to take our 4 colors of light and we're going to split it even more into a bunch of different, very small frequency bands. So again, we have 4 colors that have all been split. And then there's more optics to get it over to our detector arrays. And then those are their detector arrays. If this was a little bit confusing, that's okay. This is a very complicated instrument. I showed this to someone who does optomechanical design, and they were like, oh my gosh, that is a crazy design. I can't believe they had to do that. And I guess it's important to remember they had to line up all of these optics at room temperature, and then they had to design everything in such a way that it would maintain that alignment at 7 Kelvin, right? They had to design it in alignment at room temperature so they could do all the testing and stuff. And then it still has to be in alignment at 7 Kelvin. And as we know, the size of everything changes when you go down to a super low temperature. So that is the medium resolution spectrometer. And I apologize that it is so complicated, but that is the nature of the beast, as it were. Anyways, just another look at that sort of in diagram format, right? It goes through the pickoff mirror relay optics, it goes through those dichroic filters, and then it goes through that IFU, and then finally it goes against a diffraction grating that then leads it into a detector array. Yeah, it's complicated. Anyways, Tom, a question?
Yeah, I got a question. Were all of these technologies available already in use in some applications and just had to be adapted, or was this mostly new technology?
That's a great question. Yes, this is mostly based on existing technology that they've just taken a step further, similar to the detector arrays, where they had used that technology on Spitzer, and then they sort of made it bigger, made it better for this system. Similarly, spectrometer systems like this exist, but this one had to be extremely compact. So that put a lot of sort of new engineering challenges that had to be overcome to get this instrument working. So yeah, existing technologies, but all the engineering had to be taken to a whole new level. Let's see, we don't have to go really into the numbers very much, but just to give you a little bit closer look at that complex IFU unit. So this is that image slicer. You can see it's basically a mirror that has been cut very precisely. So it sends images in a bunch of different directions that line up with this, this mask that they have here. And then as we saw in the video, it's well, it didn't show the these things turning, but okay, so the dichroic filter and the diffraction gratings are on wheels, and so it can select different filters, select different diffraction gratings to cover different frequency space. And so here's a look at that. Here's a closer look at that. These are those diffraction gratings, and they're on this wheel unit that can turn to select different frequencies. And so if we look at the blue, the red, and the green here, we can see the wavelength coverage of this instrument. And so in going back to the camera analogy, in order for the spectrometer to see over its full frequency space, it has to take 3 exposures. Exposure, if exposure 1 is in the short wavelength mode, then you're going to see these frequency spaces, and then exposure 2 can be in the medium, which is the green, and then exposure 3 is in the long wavelength, which is the red. So yeah, you have to take 3 exposures to look over its full frequency space. Yes, so that kind of concludes our look at MIRI. We did not cover everything. I wanted to have a slide here that just talked about like the stuff we didn't go over. So we didn't really go into much about the cryocooler. The cryocooler obviously is a sophisticated instrument as well. That had to be very efficient because it's got to last a long time, hopefully almost 10 years. We didn't talk too much about the device physics of those, how those detectors actually work. There's a whole readout system. So after light hits the detectors, what happens next? Well, it has to go to a readout system. And so we didn't really cover that too much. It's got many different calibration procedures. It has onboard sources like this one here. I think this one's like a tungsten filament or something like that. So it has onboard onboard stuff like this to be sources for you to calibrate by. And then obviously it can calibrate off of some sky sources. There's obviously some sophisticated someone had to develop the software for all of this. And then of course, much, much more. We're just this is just kind of an introduction. If you're interested in this instrument, there's a MIRI encyclopedia, which is a 10-paper publication of the PASP, Publications of the Astronomical Society of the Pacific. University of Arizona has a website on MIRI, which is at that web address, ircamera.as.arizona.edu. And then, of course, there's the European Space Agency website is a good resource for more about these instruments. Okay, and then before I go to questions, I kind of want to just sort of circle back to the beginning. Why am I interested in this, this complicated optics and stuff? Again, we want to observe these galaxies at multiple different frequencies, which is what this medium resolution spectrometer is capable of, what the MIRI is capable of. And then we want to know what's going on with the star formation rates of high redshift galaxies, which the MIRI can do because it is in the mid-IR regime, which can see through the dust clouds of the ISM of different galaxies. So that gets us to questions. And thank you all for your attention.
Thank you, Kyle. That was fascinating. I have a question about the mirror. When they kind of make that stair-stepped cut into it, doesn't that change the frequency of the spectrum a little bit of the light that it's reflecting there, or not?
That's a good question. I think the answer is no, actually. I don't think it does. So yeah, unlike like a diffraction grating where the sort of sending light off in different directions is based off of the frequency, sending light off in different directions is based on like, the visual plane of your image actually, right? So, if, you could map this to say like, a detector, a sensor on your camera, which is like a square thing. And so instead of just being flat, it's instead has all these weird slices. And so that's going to send the light in different directions based on sort of where it is in your image, physically in the spatial regime.
Okay. Any other questions out there from the participants in the background? By all means, please ask your questions.
Yeah, I've got a real general question about JWST. Do all these instruments, do they have a lot of spare parts? What would it take if there's, let's say there was a launch failure? What would it take to put together a whole new telescope?
Oh, that's a heck of a question. Yeah, I mean, I was watching some of the, some of the interviews and stuff about Miri and the other instruments. So, I mean, only one of these exists, only one Miri exists, but of course, different subsequent parts of it exist. There's probably some spare mirror panels here and there, but yeah, to build an entirely new JWST, we're talking about years. Yes, some of the work is already done because, design work and testing, is completed. But there is no spare JWST sitting in a sitting in a hangar somewhere, as far as I'm aware. And part of that is just because all of this had to be put together and constructed in one giant clean room. There's just not that many facilities that can do this work.
I'm kind of surprised they don't have an actual mock-up that they can troubleshoot should there be a problem once it's launched, kind of like they do with most shuttle or space things involving astronauts, where they on the ground, they say, okay, we've got one, you're having this problem, we can go back, we can look at it, maybe backtrack what's going on. Or is that all theoretical then, that they can do it, they don't need a mock-up?
Well, what I can tell you about this instrument specifically is that it was designed modularly. So basically, someone did like an overall system design of the instrument, and then the different parts, the different mirrors, the detector arrays, those were all built somewhere separately. And then the parts sort of came together, and then it was someone's job to sort of start integrating these different modular parts into one system. And so if they wanted to sort of build another one, I think they would have to do that step again, do that sort of that last step again, where they're integrating stuff together. And, all of these instruments are built to such precision that, no two pieces you build are going to be 100% identical. If they have like a spare mirror for a particular piece of the optics, they would still have to sort of do all, test that spare mirror and sort of probably do some like polishing to get it to be within the specs that they want. So yeah, the precision necessary here, I think, is part of why there's no sort of spare, because there really couldn't be a spare. Everything's measured down to such low precisions that any part you were to swap out would have to be retested and reintegrated.
I have a question.
Nice presentation, Kyle. Do you know, can they update the software remotely?
Yeah, I'm fairly certain that they can. I'm sure there's some low level stuff that they can't mess with. I mean, Hubble is like still running some software from the 1980s because it's so low leveled and it's so level and it's integrated on basically the hardware level. So there's definitely some hardware level software in here that can't be changed, but there's a bunch of top level software that they absolutely can manipulate. I think Rick, you had a question?
Yeah, that light splitter thing has me fascinated. Can you go to that slide again?
Sure.
The light splitter.
Oh, the image
That
slicer?
one.
Yeah.
That middle part there, the exit pupil mask, is that all lined up before they launch, or is that adjustable in space too?
No, this would be lined up before launch. Yeah, the the optics of, the MIRI system are, very, very complicated. So they would have to line all this up after launch. And, they will have small amounts of tolerances on some of this stuff, but not a lot. There isn't much in these instruments that has like sort of adaptability or shiftability.
They must have done a shake test before they took off.
Absolutely, absolutely. They would have done a shake test. They would have done a bunch of different temperature tests. They probably shook it in testing. They probably shook it much harder than it will actually experience during the launch. So they'll shake it. They'll get everything up to specs. They'll test it. They'll shake it, and then they'll do all the testing again. Make sure that nothing changed.
And what's the life expectancy for the telescope?
10 years. 10 years is the life expectancy. So that's kind of the math that they've worked out for the propellant. And I believe, this instrument's unique because, of course, it depends on that cryocooler surviving. But I imagine that they've built that out to last like a similar amount of time, around 10 years.
Would there be any effects from like solar flares or anything like that?
Ideally not, right?
Okay.
Ideally, that big solar shield should protect everything from anything coming from the sun. It's a multi-layer, and I'm sure that over that decade, like some of these layers are going to start to deteriorate. But overall, it should be extremely quiet on the cold side of the telescope. Let's see. How far out from Earth is the Lagrange L2 orbit? That's an excellent question. I don't know off the top of my head. That might be something to look up. But yeah, that's a good question. It's further. They might have shown it on that video, but it's significantly past the moon. They have, let's see, distance 1.4 million kilometers. Yeah, 1.4 million kilometers is the quoted distance here from Earth. So that's pretty far out there.
Will it always be in the shadow of the Earth, or will it see sunlight most of the time? And is that sun shield that's reflective? And what's the diameter? Maybe you could pick it up. It might be a decent magnitude. You might be able to see it even.
Oh, that's a great question. Well, in answer to your first question, the sun shield, this is what's great about that Lagrange 2 point is that the Lagrange 2 point orbits with Earth, right? So, and then the James Webb Space Telescope is orbiting the L2 point. So the sun shield will just always be facing the sun and always facing the Earth. So the telescope will never be facing towards the sun or the Earth. That the sun shield's always going to protect from that. As far as how big and what the diameter is, the diameter of the sun shield is not dissimilar to the wingspan of like a jetliner airplane. So I wouldn't quote meters off the top of my head for you on that, but that's the order of magnitude we're talking about as far as size. And then as far as brightness, I don't know. That's a really good question. I'm sure someone could figure that out. But yes, it is reflective.
We'll see.
Yeah, we'll see.
Or we won't see.
Or we won't
Somebody
see.
will. Who will be first?
Okie doke. Any of our other participants have any questions? By all means, populate the Q&A site if you want. Okie doke. Kyle, I think you have baffled them. I know that My Lord, what a complicated piece of hardware.
Oh, absolutely.
Gee, me Christmas. The alpha geeks that worked on this are impressive. I mean, you included. You're an alpha geek and you're impressive too. Any other questions? No more questions. I tell you what.
Are they working on the next gen after James Webb?
So I don't know whether you're aware, there's something in multiple fields of science called decadal surveys. And so astronomy has a decadal survey. What the decadal survey is basically they ask all of the top astronomers what their priorities are for the next decade, particularly when it comes to funding. And so the Astro 2020 Decadal Survey just came out. And so they've defined one of the big things that astronomers just in general in the US want funded is a new VLA, which is ground-based radio astronomy. So there's something called NGVLA that NRAO is working on. And then also they have defined sort of a new space telescope specialized in a different frequency regime. Obviously, this is very early stages because the decadal survey just says like, this is what astronomers would like funded. This is what they'd like to see in the next space telescope as far as sensitivity and frequency. And so then it tons of work has to go into figuring out if that's feasible, and then how much funding it would take. So the answer to answer your question, concept and design work is happening on the next space telescope, but it is not funded.
I think this one used up the kitty for the past 30 years.
Likely. Yeah,
well,
this project must succeed for sure.
Oh, yes, please do. It'll break our hearts if it does not. It's going to be looking at some really incredible stuff. If Hubble was as good as it was and Spitzer was as good as it was, this is just going to just be so exciting to see the data coming back from this. And speaking of the mid infrared, and this is looking back so far, how much of a red shift is possible for something to happen. I mean, if you could go all the way back to when you had first light or first object, what is the redshift frequency capability? Can it go into long wave radio or only into infrared?
That's a great question. I mean, you're essentially asking what is the redshift of the Big Bang?
Pretty much,
right?
I guess. Yeah.
Which is perhaps a loaded question. But let's take a look here. Let's see, redshift of the Big Bang. I remember looking this up not too long ago. I mean, it's at a pretty far redshift because we have to imagine, we have to remember that there was a ton of sort of there was a ton of things going on before actually the first galaxies existed. So I think it's it's either in the hundreds of the thousands. Gosh, I'm not finding it on a cursory search. That's a really good question. But yes, there is a definitive. Possibly.
Considering it's all just frequency.
So the project that is looking, I mean, so CMB, is obviously the radiation from the Big Bang, and the CMB was studied pretty closely, especially in the 90s. They were learning as much as they could about the CMB and what they could learn from that. But yeah, so off the top of my head and on a cursory search, I don't have the answer to your question, but you're absolutely correct that there is a as far redshift as you can look, right? There is an end to the redshift sort of timeline. And I mean, it depends on what light you want to look at, right? So for us, the light from those first galaxies is going to fall into the into the frequency space of JWST. But yeah, good question. I'm the wrong person to ask, but very good question. Yeah.
Thank you.
Tom,
Yes.
I know that Tom Marsden, in working on his PhD work, was working with very low frequency antennas down around 10 megahertz or so. These are big, huge ground-based arrays, and I think they had very little directivity, but it's a very low frequency.
I would think that the CMB would, yeah, because it's the original, I mean, it's basically when light first started or energy started is because light is a frequency concept for our visual versus the infrared versus X-ray versus radio, and the spectrum of radio even it's the first wave that hits you, that long sinusoidal period of frequency. I wish I'd have been doing this when I was studying physics in college. I'd have gotten better grades. Oh, this really opens up a lot of, I know what that means now. I understand that. So yeah, it's fascinating. Oh, this is interesting. And like I said before, it's just, oh, please launch. Oh, please get out to L2. Oh, please open up. Oh, please mirrors don't glitch. There's like I said, there's only 1,000 things that have to go right. So, okay, any more questions? I don't see anything in the Q&A. I thank all the participants for listening in. I thank my club presenters for presenting, and for Rick and Jack for showing up. Take good notes there, Jack, I hope. I'll pass them on to Rick. And Kyle, I want to thank you again for presenting tonight. That was fascinating. That was really good. And if you don't mind, we will call upon you again to give us an update on something when you have something to update us on. So
sounds good.
I will be in touch. Otherwise, you know what happens. We get to hammer out of here. You all have a good night, good weekend, what have you. We'll talk to you later. And remember, January is the next meeting. Hopefully it's going to be at GCU, and we will Zoom with or without GCU. Talk to you later. Meeting's adjourned.
Thanks, everyone.
Thank you. Bye.
Bye-bye.